Merry Combinatoric Christmas! In this video, I'm going to present and discuss a combinatoric problem in the context of a Christmas ornament. Christmas is a great time to see lots of striking geometric decorations like Moravian stars, polyhedral ornaments, and patterns in lights and color. These are often rich in symmetry. In the forthcoming problem, we'll have choices of colors for a pattern on a spherical ornament, and we'll need to figure out how many different ornaments are possible given the various color choices and configurations. The spherical ornament will have a surface pattern derived by projecting an Archimedean solid onto the surface, so it'll be rich in symmetry. Here's how it will be constructed. We'll start with a dodecahedron, 12-sided solid with regular pentagons for sides and highly symmetric due to all faces, edges, and vertices completely regular and interchangeable. It is one of the 5 Platonic solids discussed in geometry classes. These are sometimes used as 12-sided dice in various games. I'm showing it rotating on an axis that showcases several of its views: face first, edge first, vertex first, and in between. Now we're going to modify it from a Platonic solid into an Archimedean solid by grinding down its corners. Since 3 edges meet at each corner, the corners will become triangular in the process. We're going to go all the way until we again get a pentagon, and now we have 12 regular pentagons as well as 20 equilateral triangles. Now that we've ground the sides all the way down, we have a solid known as an Nkosi Dodecahedron, and it has the remarkable property that its edges form 6 separate decagons that go all the way around right in the middle like so many equators. So next, we will project these edges out onto the surface of an imaginary sphere just enclosing the Nkosi Dodecahedron, and now you can clearly see the 6 intersecting great circles. Since we no longer have any use for the underlying Nkosi dodecahedron, we'll replace it with a sphere, and now we'll have 6 great circles on the surface of a sphere intersecting in a highly symmetrical manner. It has the same symmetry as the dodecahedron that we started with. So for the ornament in this problem, I'm going to color 2 rings red, 2 rings green, and 2 rings gold. I've chosen the rings randomly, and this is just one of many ways to arrange the rings. So for the first question, A. How many different ornaments are possible with 2 red, 2 green, and 2 gold rings if we can't tell apart ornaments that can be rotated into alignment? So what you're seeing here is 2 ornaments starting out choosing 2 different arrangements for the red, green, and gold, and then a sequence of rotations that brings them both into agreement. For the next 2 problems, we're going to think about hanging up the ornament. So as you can see, we're putting a hanger directly centered upon one of the 30 vertices on this ornament. So question B is how many different ornaments are possible if we hang the ornament from one of its vertices, and now it can only rotate on that one axis. And finally, for problem C, we're going to put the hanger directly centered upon one of the 20 triangular faces of the ornament, so question C is how many different ornaments are possible if we hang the ornament from the center of one of its triangular faces, and rotations are now restricted to that axis only. So if you would like to solve these problems without seeing my answers first, then stop now and go get to work on them. I'll give the answers and explanations in the slides ahead. For problems like this, there are generally 2 approaches that I can think of. The first approach is often taught in probability. It involves first simplifying the problem by specifying a reference position to start from, then building up the final product by making the choices in a series of steps, sometimes involving a decision tree. I'll use this approach on problems A and B. The second approach is an argument from symmetry. First we look at how many patterns are possible if the ornament were completely oriented and stationary, and that's a traditional problem involving permutations with repetitions, and there are straightforward solutions, even formulas for doing that. The next step is to see which of these patterns are equivalent under the various positions into which the object can be rotated, and the patterns will fall into what is called equivalence classes, which may or may not all have the same number of elements, but when they do, the answer becomes a simple division. So, for problem A, let's put the colors on in stages and specify a reference position. First, we'll specify a reference color, say red. Pretend only 2 red rings are there. They will intersect at diametrically opposite poles. Bring these red poles to a reference position, say along the x-axis equidistant from the origin. Now note that the rings have large jaws and small jaws. Let the y-axis pass midway through the small jaws and the z-axis midway through the large jaws. Here's a sketch of approximately what you'll see looking down the z-axis through the large jaws. Note that in this orientation, the two red rings have symmetry under a 180-degree rotation along any of the x, y, or z axes. These rotations, plus the identity rotation, form a Klein-4 group for those of you who like group theory. Now, if you add back the other rings, you'll see something like this. The 4 black lines are part of the other 4 rings. Now let's make an interesting observation, which is the key to solving this problem. A 180-degree rotation around the z-axis swaps the colors of the vertical lines, but leaves the colors of the diagonal lines alone. A 180-degree rotation around the y-axis swaps the colors of the diagonal lines, but leaves the colors of the vertical lines alone. A 180-degree rotation around the x-axis swaps the colors of both the diagonal lines and the vertical lines. Now, there are 4 black lines in this diagram, and we must select 2 to be green and 2 to be gold. There are 6 ways to do this. All 6 are equally likely if you randomly assemble the ornament. First, let's look at symmetric arrangements of the colors. If the colors of the diagonals are both green, then the colors of the verticals are both gold, and this pattern has 180-degree symmetry on any of the x, y, or z axes. There is a 1/6 chance of this. Similarly, there is a 1/6 chance of having gold diagonals and green verticals. That takes care of 2 of the 6 arrangements. The remaining 4 ways have 1 green vertical line and 1 green diagonal line, and vice versa, with the remaining lines yellow. The key observation is that any of these 4 ways can be made to coincide with the pattern below by choosing rotations correctly. If the vertical lines are not the right color, a 180-degree rotation around the z-axis will correct that, while preserving all the others. If the diagonal lines are not the right color, a 180-degree rotation around the y-axis will correct that while preserving all of the others. We conclude that for problem A, that there are 3 different ornaments possible. There is a configuration with green poles centered within the large red jaws with Klein-4 symmetry and probability 1/6 when assembly is random. There is a configuration with gold poles centered within the large red jaws and Klein-4 symmetry and probability 1/6 when assembly is random. The remaining configurations without rotational symmetry can all be rotated into the same configuration and occur with probability 2/3 when assembly is random. Now for problem B. Problem B, the hanger mounted on a vertex restricts the ability of the ornament to rotate. We'll use the hanger as a reference position by placing it on the left-hand side along the x-axis. The configuration no longer has Klein-4 symmetry like it did in problem A. The hanger is ruined at by making one of the vertices distinguishable from the others. The only symmetry occurs with a 180-degree rotation around the x-axis, and that holds whether or not the rings that meet at the hanger are the same color or not. We'll do 2 cases, one in which the same color rings meet under the hanger, the other in which different colors meet. If the hanger is on a vertex where 2 same color rings meet, then there are 2 pairs of colors inside the large jaws. There are 6 ways to configure them, as we saw in problem A. If the diagonals are the same color, the verticals will be the remaining color, and the configuration will have symmetry under a 180-degree rotation along the x-axis. If the diagonals are not the same color, the verticals will not be either. Since we're allowed to rotate 180 degrees along the x-axis, this will swap the verticals and also swap the diagonals, so we have 2 equivalent patterns from the remaining 4 arrangements. These patterns can be distinguished by noting that in one arrangement, the same color angles always point down. In the other arrangement, they point up. To summarize, when the hanger is on a vertex with 2 same colored rings or poles, there are 30 vertices. 2 of them are red poles, 2 of them are green poles, and 2 of them are gold poles. There's a 1/15 chance of each. Then the symmetric arrangements have a 1/6 chance of each with a pole centered in the large jaw. 1/15 times 1/6 equals 1/90, and there are 6 color possibilities. 3 choices for colors under the hanger times 2 choices for pole colors in the large jaw. The non-symmetric arrangements consist of up-pointing color angles, 2 out of 6 possibilities, and down-pointing color angles, another 2 out of 6 possibilities. 1/15 times 2 out of 6 equals 2/90ths, and again, there are 6 possibilities, 3 under the hanger times 2 up versus down. Now let's look at what happens if the hanger is on a vertex with different colored rings. There will be a pair of rings with the same color and 2 singleton colors in the large jaw. There are now 12 ways to arrange these, and they pair up into 6 sets of equivalent patterns, which are the same under a 180-degree x-axis rotation as shown. The first row shows a set where the verticals are the same color, and another set where the diagonals are the same color, further to the right. The lower left shows configurations where there is an upward pointing yellow angle, and the lower right shows configurations where there is a downward pointing color angle. In all cases, a 180-degree rotation around the x-axis converts one equivalent pattern into the other. Now we can summarize what happens when the hanger is on a vertex with two different colored rings. On any ornament, 4 vertices each will have one of the 6 color combinations: red-green, red-gold, green-red, green-gold, or gold-red, gold-green, as colors for the top and bottom of the large jaw when brought into the reference position. This starts us with 6 possibilities, each with 4 vertices out of 30 total, or a 2/15 chance. Then there were 12 equally likely choices for the remaining 4 rings, which we broke down into 6 sets of 2 patterns for each ornament, 6 each with 2/15 chance in step 1, times 6 each with 1/6 chance in step 2, yields 36 ornaments, each with 2 chances out of 90. Now taking results for all cases together, problem B had 36 ornaments with 2/90ths of a chance if the hanger was on a multicolored vertex. If the hanger was on the same colored vertex or a pole, there were 6 symmetric ornaments with 1/90th of a chance, and there were 6 non-symmetric ornaments with up-down configurations, each with 2/90ths of a chance. Total is 36 plus 6 plus 6 is 48, and the probabilities sum to 1. As you can see, 36 of them with 2/90ths, plus another 6 with 1/90th, plus another 6 with 2/90ths. That's 90 out of 90. Now for problem C, I'll take a different approach, and there will be no diagram since this will be an analytical solution. We solved A and B with spatial reasoning and decision sequences. That is possible for C also, but the decisions are getting more complicated. So instead we'll use a symmetry argument for problem C. Actually, it is a lack of symmetry argument. There is no symmetry about the axis for which the ornament in problem C can rotate. If there were 3 same colored rings, we could have symmetry, but not with just 1 or 2. I'll have an equilateral triangle surrounding my hanger that looks different in each of the 3 alignments that occur as we rotate it. Therefore, any ornament comes in sets of 3 equivalent patterns when rotated into the 3 equivalent positions of the triangle upon which the hanger is mounted. If we couldn't rotate the ornament, ordinary permutations with repeats would apply, and you could look up a formula for that. We would have 6 factorial for the total rings divided by 2 factorial for each pair of same colored rings, or 6 factorial divided by 2 factorial 3 times, and that's equal to 720 divided by 2 divided by 2 divided by 2, and that's 90 ways to select colors for rings on the stationary, fully oriented ornament. Since we rotate on a triangular face which comes into alignment 3 different ways per full rotation, these 90 arrangements breaks down into sets of 3 equivalence classes when rotated into the 3 equivalent positions of the triangle upon which the hanger is mounted. These 3 positions all produce a different pattern since there is no symmetry under this rotation with 2 rings of each color. So we've got 90 configurations divided by 3 configurations per ornament, and that's 30 ornaments in all equally likely. So once again, thank you for watching. I really enjoyed making the animations of these colorful geometric solids, and I hope you enjoyed watching.